Just share my screen. So, hello everyone. Welcome to week 7 problem solving session. And this session, let's look into the problems which Professor have posed this week. Yeah, so the due date is on 12th. Please take that in mind. And if you look at those questions, so most of the questions are comprehensive based question. Since this, all of this, I think from week 5 onwards or week 6, all of the content, if you have seen, are mostly related to the research which Professor Felix did during their PhDs, or also during or also which is currently is doing, mostly related to that. So you don't have to deeply look into uh, like what kind of strategy they have used. You just need to skim through it, and also you just need to see what are the conclusion and why they have chosen those methods. So you need to focus on that. You don't need to mug up the equations. Let's look at the some of the slides first, and if you see, so let's start with lecture 31st. Yes. So they have talked about robotic assistants. These are literature review kind of stuff, right? So since he discussed, like there are like some 10 to 15 systems are there. Okay, so you don't have to mug up this part, but you just need an idea. Okay, there are these systems are available, okay, and what they use, something like that. So you don't need to go much deep into it, but you need to know why we are doing this. Okay, so basically, let's go to the lecture 34. Okay, not lecture 35. Yeah, so lecture 36, if you see, lecture 36 is mostly related to his PhD work, where he have shown you like how he designed this robotic device, right? And like why he have chosen this 4 degree of freedom, and how, so this is the DH parameters, and like how he have chosen this feedback thing. You just need to know this. Okay, you don't need to uh, go through. So this is for your information only. Okay, so we won't ask you some questions on coding on this part. You just need to know what kind of strategy they have used. Like here they have used adaptive PID controller. So how they have used this adaptive PID? So they have used this control scheme. This control scheme consists of two parts, where this is the equation, which is simply a PID controller, whereas US is something which is related to sliding mode control. So you need to know the concept wise. So the concept should be clear. So the concept, if you go to lecture 33, so lecture 33 is all about the concept. So you just need to focus on the concept. So like here, let's say he tried to introduce this concept called sliding mode control, and here you have chosen that this is your control input, and this is F is your something like a disturbance, right? So you just need to know how this disturbance, and this is when the disturbance is zero, and this is where when we have taken a sinusoidal 2t disturbance, right? So how to tackle this kind of thing? So he proposed this something lot of like a sliding mode control. So this is what we desired, but why we desired? Because when you plot this the reduce when you plot this equation, you will find that the x will decay with respect to time. And so please go through this concept, like what is sigma. If you don't know it, you can ask in the group discussion channel, or you can rewatch the video again, or you can uh, you can read the books. I think as Felix have already shown it here. So like here, so this is before sliding mode control, and so you see these are the disturbances which you got, and after using this sliding mode control, this is what you got. So that yeah, so this disturbances will get reduced to zero, something like that. So you need to focus on the base concept part. So I what I would suggest is focus on lecture 33 in this whole week. I think this is what on concept I'm talking about on the concept part. So please go through this lecture thoroughly. And coming to lecture 34, so lecture 34 is like a more advanced version of lecture 33. Like here they have used higher mode controller. So in this case you need to understand like why we have chosen this, what happened that. Okay, and you don't need to mug up this results. Okay, so there is this something like chattering effect are there. So how they have reduced this chattering effect. Yeah, so don't need to go through the experiments part. Okay, and yeah, so if you look into this question also, there are not much on the, so they wanted to just to know like why we are doing this, what is the main goal of designing the sliding mode controller. So something like that. Okay, so you just need to understand the reason like why we want to choose particular method. Okay, don't need to go through like how a certain method works. Okay, so let's go over the some. So I made some questions. So these questions can be helpful in your final exam, because I have taken this from the last year's problems. Okay, so this is the question which I am going to solve here. I mean, these are not a numerical based question, but these are again a theory based question. Please, so I will share this all the slides with you. Okay, don't need to worry about. You don't need to record this video. Okay, so you don't need to watch it again. So I will answer each and every questions and also be available to you. Let's start. If you have any questions, please do ask me. Let's see if anybody has. Yeah, I think so. The next week will be our last week. Okay, but the next week I will cover some questions. Will cover some last year question, not last year question, but I will make some questions so that which will be helpful in your final exam. So let's look at the first question. So this is let's read out what it says. Which is the robotic assistant? Which is yeah? Why is robotic assistant necessary in uh, percutaneous kneeling intervention? So why it is needed? So now to know like, so let's look into the options one by one. So to improve the target reaching accuracy, because I mean if you look the soft tissues, like let's say Professor Felix discussed regarding the pancreatic cancer, right? If you want to reach something like uh, let's say the pancreas, okay. So if you make a hole and so you need to be more careful, right? Because there are so many soft tissues which are attached to your pancreas, right? So first option seems reasonable to me. Let's look into to aid the physician. Uh, I don't think so, because but there are other instruments also. So of course, need to aid or to avoid. I think you're right. I think B option is also right, because we need to aid the physician, right? Because let's say if you have some body part, like let's say a pancreas here and something like here, and there's something like here. So a clinician can't like put screwdriver or a you want to read something like here, and this is the only way which can go, right? Or you can go like this, but like a physician or a doctor can't place his hand like this, right? We need some kind of a curvi curvature or some kind of instrument which can bend its path, right? So B option is also right here. A, so to improve target reaching accuracy, A is right. B, to aid the physician, yes. And C, to avoid anatomical obstacles. So like let's say this is soft tissue. Let's say this is again a soft tissue. So you won't. So the clinician won't puncture this thing and like this. They can't reach like it. So they need to puncture this soft tissue, right? So again to avoid an anatomical obstacle, right? So here option will be D, all of the above, right? So D is your right answer here. And the next. So what is the imaging feedback modalities? Modalities is something like which where you where you will imaging feedback modalities, right? So used in robot assistant percutaneous intervention. So so they wanted to know like what are the imaging feedbacks you can use. So let's say you have this some kind of a your this is a needle and this is something called a cover. I think can't remember. Forgot his what this name I think. And you wanted to bend this needle in real time, right? How to do that? So and you wanted to bend the end effector, right? Like this and but yeah, so you can bend it, but you wanted to know what is the end effector position, right? So so that this position can uh, actual position can act as a feedback for your control, so that your motor can change accordingly in order to let's say reach some position, right? So the question what he's asking is like what kind of imaging technique, right? So there are multiple ways to know the orientation of this end effector, like how it is oriented with respect to its base frame, right? There are MRIs, right? MRI is basically magnetic resonance imaging technique, where like you need to go through some kind of a dome kind of a structure, right? And something like that, right? And there is a CT scan, basically a bone scan, and I think US is basically ultrasound. Okay, so to get this kind of to get the answer kind of a question, you need to go to the lectures, right? So let's look into the lecture 36, which is I think the last lecture in this week. And yeah, so this is design 2, and they have they talked about the actuation. Yeah, so see that they have used a shape memory alloy, and let's see if they have shown some result on this page. They haven't mentioned it here. That you need to let's go to lecture 35 and see if, so these are some techniques which they so this is the first design they have made, and the shape memory, so they have used shape memory alloy as their actuators. And yeah, so if you look, so they have used a multimodal technique here, feedback control strategy. So they have used ultrasound basically, ultrasound which I was talking, electromagnetic. So for his research, Professor Felix have used these three methods, which is the vision based method, electromagnetic method, and imaging based method. But in the question, it is written CT scan, MRI scan, and ultrasound, all of them. Which are the image modalities used in robot assisted precautions? But let's say if they ask what are they used in their research, then your answer will be different. For that, I think you need to go to lecture the 31st is the you see yeah, you see the image. So they have used ultrasound here, and they and so they use MR, which is I think magnetic resonance, I think, and feedback control needle approved like this. And do is some of them use ultrasound, some of them use MRI also. Okay, so some of them mentioned like what they have used. But if you say like if you want to, because MRI and CT scan takes time, okay, but ultrasound. you can you can take it in real time. Okay. So if you ask me, because most of the but if you look at the literature review slide, the first slide, and you will see most of them are using something called ultrasound. Okay. And it's a feedback based technique, right? Because that feedback technique used to run in real time. So here the answer will be C here, right? Because it needs to run in real time. For CT and MRI, these are some techniques which you don't get in real time. The data, you will get a data, but you need to do something like a post processing thing. For MRI, let's say this is your let's say this is your, something like a this is your knee, right? Your, let's say, a patella, and this is your femur, and this is the. So what they do in MRI is like they make slices, make multiple slices, they cut, right? And in order to uh, so they will take multiple images, not slices. They take multiple images, and they will take. So if you cut your leg like this, you will get some kind of a plane, right? And that plane will show some kind of a shape like this. If you cut it in a different plane, let's say a point 5 mm more ahead of posterior, 0.5 mm anteriorly, the shape might decrease, right? So what they do in MRI is like they take multiple images at different intersection, at different planes, right? So that need kind of a kind of a post processing, right? So MRI and CT can't be used as a feedback device, whereas ultrasonic ultrasound is something where I think if you have a if you have any something like if you've gone to, let's say, an orthopedic doctor, you must have seen with him that they use this ultrasound, and you can detect whatever in real time, whatever going inside your let's say a bone or a cartilage, you can see it in real time. So C is the option. And let's look into the, so this is a simple theory based question. How many degree of freedom the active needle design 2 has? So there are two design which Professor Felix discussed in his lecture. So if you go to the lecture 35, so yeah, so this is the design one thing. And if you look closely, there are two joint one and joint two, theta one and theta two. So there are the 2 degree of freedom needle, smart needle. Okay. And but in the question it is written that they wanted to know what is the degree of freedom for design two. Okay. For design two, need to go back to design two. What they have used is they have this uh, prismatic joint, right? T, and there are uh, three joint, three revolute joint, theta one, theta two, and theta three. So it's a 4 degree of freedom needle. Okay, and this is kind of a DH parameter for that. So here A is your answer. Okay. So I will, yeah, I will share this. Will share all these slides with you. This, no need to write down and every. So let's into the next question here. So the disturbances given in our research study while controlling the SMA actuated active needles are. What are the disturbances which they have created, right, while controlling this SMA actuated needle? Okay, so if you go to his last lecture where he talked about his 4 degree of freedom needle, right? This is the his last design, and he talked about like how, so like if you see like one, two, the 4 degree of freedom, 4 degree of freedom smart needle, bitter needle, and to check the robustness of the control strategy. What he did was like he introduced something like an external disturbances. Since we don't have a live tissue with us, what he used as the external disturbances is he blown air disturbance. So he blown a air to see if it's tracking that sinusoidal wave or not. Okay. So what he so the sliding mode control, what he the sliding mode control does is that it reduces that those external disturbances, right? It eliminates the disturbances. So how to create an artificial external disturbances? So what Professor Felix used as external disturbances here is a blowing air as a disturbance. I think he have also used something like a force torque sensor. So he finally introduced this force and torque at the and the end point. So there are two types of disturbances which he have introduced. Okay, and yeah. So let's see if what is uh, the option matches one of the option matches with our description on Earth. So disturbances from tissue heterogeneity and cooling, no. So he haven't used that because he haven't have that tissue. SMA hysteresis and non-linearity, no. Air blown disturbances to the SMA actuator and load at the tip. Yeah, so there are two disturbances. One is air blown and the load at the tip. Yeah. So C will be your right answer. Okay. So you don't need so there is nothing more on the mathematical side. So there is one question I think I have introduced. So I think this was asked last year, I think. So you just need to know like what kind of equation he used, right? So he used something like a closed loop inverse kinematics to control those needles, and this is what the equation look like, and you have to choose which the correct one. Okay. So, you don't need to mug up this, but there are some equation which you need to know. Okay, so just like this one, US plus U, you don't need to know. So U equation is basically it's U equation is basically a PID, KP error, KI integral of error, and KD. US is basically a sliding mode control part. So you have this KP, but again, this gamma sigma E is your sliding variable. Okay, so where was I? Yeah, so we are looking for the inverse closed loop. Yeah, so closed loop inverse kinematics. Yeah, that's what he used in his what he used to control those actuators. This was a sliding mode controller. I think if you go to lecture 35, find this kind of a lecture. Inverse kinematics control of a smart needle. So for this, he have used this equation where he controlled this Q dot, basically the joint angles at these 2 points by actuating this SMA actuator. So he heated these two actuator and he changed those angles. How he did so and how he changed those yeah. This is what the control strategy which they have used. They have Q dot is equal to J, and this is what the uh, equation which he has used to control their actuator. So I think it's B here. I think this is B because it's an addition. K is addition. K inverse X dot. Already know this, but KE has introduced because we wanted to control the position of the end effector, right? This position, the conical tip, and you know how to go from one position to another. So you know the trajectory of this point. This is what you have given as an input, and based on this input, you have used this value to get Q dot. Q dot is basically theta dot and theta. And so there are two theta one and theta two, and this is what you get. So please do remember this equation. And I think let's go to the next question here. Yeah, I think we can leave this question for the last part. So this is a this question is a bit more interesting. So consider n state and m control input in a system where m is less than n. N is the number of states, and let and m is the control input. Okay, and let x denotes the system state. Yeah, so n is number of state, right? So let x denote the system state, and s denotes the sliding variable. Pick the correct statement for pertaining to a sliding or control system. So they are asking about we need to pick the correct statement. So let's read out the first one. Order of subsystem when s is 0 is m. Order of subsystem when s is 0 is n minus m. Okay. So or and then the next option is sliding variable is of dimension n minus m. It's a sliding variable. So for that, for this kind of a question, we need to delve deep into I think it's lecture. Yeah, I think this is sliding mode control where he was talked about. And if you look at this question, there are two states, x1 and x2, right? Yeah, so there are, I think, x1 and x2, there are two states. And there is only one input, which is u. We haven't. Yeah, so there is only one input, u, right? And yeah, so this is what sliding mode. So, but he haven't mentioned like how to find out uh, order of the subsystem, which is s is when s is 0. Okay, so s denotes the sliding variable. In our case, what is the sliding variable? So this is sigma. Sigma, yeah, sigma is your sliding variable. So this is your sliding variable, sigma. And what are the properties the sigma should hold? For that, you need to go to lecture 34, I think, lecture 34. And yeah, this is what sigma look like. There are the sigma here. So this is sigma equal to 0. Sigma is 0 is basically your disturbance. Uh, I think sigma is something else. Sigma you need to 33. Yeah, so sigma is basically your disturbances basically. So for a disturbance, what the equation should look like x1 dot plus the x1. Basically, you want your x1 to be 0, and you plot this equation. Time actually. This is a state one, and you want your system to behave something like x1 dot plus cx1, because when you integrate this stuff, you will get something like x1 at the initial condition, and this is exponential minus ct. Minus ct, if you plot this on a graph, it will look like something like this, and that's what you want. You want at a particular time t, it will decay, won't explode. Okay, so this is what you want, but this won't happen due to the incorrect due to, I mean, there are, right, I mean, what are the problems which this won't happen because there is a external disturbances. There are some parameter which you haven't included in your mathematical model, right? So this won't happen always, right? So instead of getting 0, you get something like a sigma, which is basically your sliding variable, and this is a function of x1 x2. So here if you see, we have used something like fx1 x2, what a disturbance look like. But yeah, so this is what a disturbances look like. But this how this x1 x2 came. So this sigma is some kind of a disturbance, needs to be 0 at some finite time, right? This is what you need to do it. We need to reduce it to 0, right? But yeah, but that is not the question. The question is, so that is what we are talking about. So this is sigma 0, and this is sigma dot 0, which is basically the velocity or the position. So this is what we are talking about, how many sigmas we need to have, right? So here the sliding variable is sigma, and what will be its dimension? Is it n minus 1 or is it n plus 1? So if you look closely, the question which is given as an example in lecture 33, there is only one sigma. There is only one sigma, and yeah, and this sigma is basically n minus 2, n minus m. There are two states, right? X1 and X2, and m, which is your input. There is only one input. So 2 minus 1 is 1, right? And that is what sigma is. We have only one variable. So D is your option, right? And coming to the order of subsystems, I don't really know if it's B or I will. So I can't confirm regarding A. So there will be two right answer. Okay, so is it B or A? I am little bit confused. So I will let you know in the next lecture. Okay, or I will while uploading this whole slide, I will mention the reasons why I have chosen B or A. So here for now, C is the right answer, and I will look into the A and B also. And this is the question: which one is the best method to make control input continuous and smooth? Okay. So what is the best method to make our input continuous and smooth? Is it a sigmoid function, sigmoid or a quasi sliding motion? So or an asymptotically sliding mode or an integral sliding mode control or a higher order sliding mode control? Sigmoid function is basically yeah, I mean it's basically going up and down, up and down, up and down. It's like that. Whereas asymptotically might work, but what Professor Silix have discussed here is need to use something like higher order sliding mode control, right? Higher order sliding mode control. Because that's what if you so these are the some of the discontinuous. This is called a chattering, right? So while introducing this sigma double dot, the higher order the sigma double dot, they have reduced this chattering, and this is what one of the conclusion which they have drawn: robust controller performance. Higher order SMC confirm finite time convergence of the system, proof of distance and time convergence. So they have also he have also proven it, right? So you will get something like a continuous system. You won't get that chattering, right? The chattering is uh, will fall under the discontinuous discontinuity. So for continuous system, D is your right answer. I think this is the last question. Which of the statement is true? The relative degree is equal to the system order, which means that the system does not have any internal dynamics. Super, yeah. For so let's look at the each option. So let's say if you have a super twisting algorithm as a discontinuous control. So super twisting algorithm means, let's say you have this, you wanted to go something like this, and they're talking about the super. So if the algorithm, if the trajectory is super twisting, so this is some kind of a super. So there is a twist and turn at every end, right? They are telling that they are very discontinuous. But in my previous uh, question, I have told you that if you use something like a sliding mode controller with higher, yeah, with higher sliding mode. So if you have a higher order sliding mode controller, you can run it continuously. Don't have to face continuous control. And coming to C option, the reaching phase meant by the system state trajectory. So I think this C option is I haven't framed it correctly. Okay, so this is an incorrect statement here. So I think if you look to some of the 33 it is. This is what the reaching phase look like, and this is what the sliding phase look like. Okay. The reaching phase is where you go from the initial position, which is actually here x naught is 1 and x2 is minus 2. Right. So this is what the initial position, and this is where you go what is this position? This position, this phase is called a sliding phase. And if you go to lecture 34, and you will find that this is what your question look like. So at time t equal to 0, this is where it is, and this is rotating itself, and this is where you are reaching. Sigma dot and sigma is 0, which means that the system is quite stable and continuous at this point. So when you use something like this, it will rotate and come to this point, and it will follow this. Okay, so this is what the stable sliding trajectory look like. I think it has a dimension of 1 because it's a straight line. It's not a sliding surface, but it's a straight line. It's a 1D. So, the reaching phase meant by the system trajectory, I think it's a wrong statement, but need to know that the reaching phase is something where you go from here to where you first struck this stable point. And let's go to the A option. The relative degree is equal to the system order, which means that the system does not have any internal dynamics. I think this is a bit more comprehensive. I think for this kind of a question, you need to dig more deeper. So the relative degree is equal. So let's say if you have a, yeah, if you have a 1 degree of freedom system, if you have not 1 degree, but if you have some degree of freedom equal to the system order. Let's say if you have something like n links, so this is n link, link one. The relative degree is equal to the system order. So the relative degree is basically how much relative degree you have, which means that the system does not have degree is equal to the system order. So how much relatively changing? Yeah, I mean relative degree is basically is equal to system order is basically the degree of freedom, which means that the system does not have an internal dynamics. So like if you have, and yeah, it's the same thing. You have joint kinematic, uh, the end effector is a joint, something like a joint space, and something like a Cartesian space, right? So if the joint space and Cartesian space are equal, then the system does not have any internal dynamics. So then it means that the system does not have any loose end. Okay, so if you have each actuators at each point, and that is equal to whatever end position you need to reach, how much degree of freedom it has. Let's say if the end effector has given you x, y, you need to reach x, y, z, and also you need to reach at that particular angle at alpha, beta, and gamma. Then it has a 6 degree of freedom. And if you have, let's say, 6 link, then it is always equal. These 6 links can be easily controlled, right? But let's say if you have, if you don't have any actuator at, let's say, at one point, then this have any internal dynamics which can affect the other point. That is what the A option is right here. Okay. I think this is the last question, and yeah, I will send the reason. I will also correct this part. Okay, I will not correct it, but I will give you the reason behind why B and why A. So there are two correct options here. That share with you. Yeah, so I will share with you in the next week, or you can find it in the problem solving session. You can find my recordings and also these Excel slides. Okay, you just need to go through it, click on this part, and you will get all the YouTube videos and also for the presentation folder. Okay, I think there's nothing more to talk about. Let's so please yeah, so what is the key feature of sliding mode control? So you can easily find it from this. You just need to go through those lecture slides, and you can get an answer. And let's see what week 8 is about. So again, you see there are mostly, yeah. So in the CLIK, which is closed loop inverse kinematic algorithm. What kind of thing they have used? Is it Jacobian pseudo inverse method, Laplace method? So you can easily get this thing how to get. You can easily get this equation by going through those lecture slides. You don't need to even get to the lectures for solving, but please go through the lectures so that you can get an understanding like why we have used a particular method over the other. I think that's it for today's session. I think stop here. We'll stop the recording.